We'll start this video with the definition of a radical. And so we'll say that if n is a positive integer that is greater than 1, and a is a real number, where real numbers are just any number you can think of that exists on what we call here a number line. So for example, -2 all the way to 3, they all exist on the number line. And in between 1 and 2, you have the square root of 2, which also exists on the number line, along with pi, which some of you may have seen before. And so if n and a meet those memberships, then we'll say that the nth root of a is the same as a to the power of 1 over n, where n is the index and a is called the radicand, and this symbol here is called the radical. And we'll call this left side of the equation the radical form, and the right side is going to be called the exponent form. And so from this definition, we can see that a radical is just simply another notation for the first exponential form that we looked at in our previous rational exponent video. However, there is one exception to this notation. That is, for square roots, we can just drop the index. Now let's do a few examples, and I'll ask you to write each of the following radicals in the exponent form. So feel free to pause the video if you need to. So to start, let's first again recall that if we have the nth root of a, then that's the same as a to the power of 1 over n. So then for a, if n is 4 and 16 is a, then we'll just write it as 16 to the power of 1 over 4. Same idea for b, all we're doing is finding the values of n and a, and we're substituting them into the formula. So here, n is 10, and a is 8x, so we write it as 8x all to the power of 1 over 10. Now for c, now let's remember for c that if there is no written index for the radical, then that is just a square root. And so we write this as x squared plus y squared all to the power of 1 over 2. Now from our previous video on exponents, we should know that only the term to the left of the exponent gets the power, and so again we have to be careful with our parentheses. Now let's walk through some evaluations of radicals in rational exponent form, and I suggest that if you want to tackle these on your own and haven't watched my video on rational exponents, you take a look at that. So for a, we already know that we can write this as 16 to the power of 1 over 4, and now we're looking for some number to the power of 4 equals 16. And since 2 to the power of 4 equals 16, we'll say that 16 to the power of 1 over 4 is 2. Now there's a general rule about evaluating square roots when we're generally radicals with even indexes. And that is when evaluating square roots, we always take the positive answer. And if we want a negative answer, we would do the following in this case. Negative 4th root of 16, which equals negative 2. And now for b, we can do the same thing. We do negative 125 to the power of 1 over 3. And now again, we're looking for some number to the power of 3, which equals negative 125. And we should know that if 5 to the power of 3 equals 125, then negative 5 to the power of 3 equals negative 125. And so here our answer is negative 5. Note that we don't have a similar rule for radicals with odd indexes, such as the cube root in our second example, because there will never be more than one possible answer for a radical with an odd index. And so we can write this general rational exponent in terms of radicals as a to the power of m over n equals, in parentheses, a to the power of 1 over n all to the power of m, which equals the nth root of a to the power of m, or a to the power of m inside the parentheses all to the power of 1 over n, which equals the nth root of a to the power of m. Now let's take a look at some properties of radicals. So if the index is a member of positive integers greater than 1, and a and b are a member of the set of real numbers, then we'll say that for the radical, if the index and exponent are both n, then that's the same as just a. And for the second property, if we have the nth root of a times b, then we can write that as the nth root of a multiplied by the nth root of b. Now for our third property, if we have the nth root of a over b, then we can rewrite that as the nth root of a over the nth root of b. And so our quotient and product rule are very similar. Now also note that while we can break up products and quotients under a radical, we can do the same thing for sums and differences. So if we have the nth root of a plus b, that's not going to be the same as the nth root of a plus the nth root of b. And same for the nth root of a minus b. We can't get the nth root of a minus the nth root of b. Next, we're going to be simplifying radicals, and so we should quickly define the simplified radical form. So a radical is said to be simplified if each of the following are true. First, all exponents in the radicand must be less than the index. So for example, if we have the third root of x to the power of 5, this is not simplified since 5 is greater than 3. and 5 is the exponent, and 3 is the index. So we'd have to rewrite this as the third root of x cubed times x squared, which just equals x times the cube root of x squared. And now we can call this simplified since 2 is less than 3, where 2 is the exponent and 3 is the index. Then second, any exponents in the radicand can have no factors in common with the index. So for example, if we have the sixth root of x to the power of 4, this is not simplified since there's a greatest common factor between 6 and 4, which is 2. So what we do is now divide 6 and 4 by 2, and so our simplified version would be the third root of x squared. Now for our third one for our simplified form, we need to be that no fractions appear under the radical. So for example, if we have the square root of x to the power of a half, that's not in simplified form. So we'd rewrite this as x to the power of a half, all to the power of a half, which equals x to the power of 1 over 4, which is just the fourth root of x. And now we have our simplified form. And for our final one, it also must be true that no radicals appear in the denominator of the fraction. So for example, if we have 3 over the square root of 5, so we'd have to multiply this by the square root of 5 over the square root of 5 so the value doesn't change. Which is then 3 times the square root of 5 over 5. Since when we multiply these two denominators, that's the same as saying the second root of 5 to the power of 2, which we can cancel out using our first property. Now you don't have to memorize all 4 conditions, because we're going to take a look at a few examples where we assume that x, y, and z are all positive, and hopefully you get the grasp of things. So for a, this radical violates our second simplification condition, since both the index and the exponent have a common factor, of which being 3. So to fix this, we have to convert the radical to exponent form, do some simplification, and convert back to the radical form. We're going to rewrite this as x to the power of 6, all to the power of 1 over 9, which equals x to the power of 6 over 9. Now we can simplify. That equals x to the power of 2, all to the power of 1 over 3. And now to finish this in radical form, we'll say it's the third root of x squared. Now for b, we can first factorize the radicand. So that'll look like the fourth root of 16x to the power of 8 multiplied by y to the power of 4 multiplied by z to the power of 12 multiplied by 2xy. Now since our index is 4, we're looking for powers of 4, and so that equals 2x cubed times y times z cubed times the fourth root of 2xy. And that's our simplified form. Now for c, already both of the radicals are in simplified form. However, there's this one unspoken rule for simplification, which is that we should have as few radicals in the problem as possible. So that means in this case that we can use the second property of radicals to combine these into one radical, and then we'll do any simplification from there. So that means we can rewrite this as the cube root of 9x squared times 6x squared. And again, getting this into the radical. And then when we expand that, we get the third root of 54x to the power of 4. Now that it's in this form, we can factorize and do some simplification. So we have the third root of 27x cubed times 2x, which equals the third root of 27x to the power of 3 multiplied by the third root of 2x. And that's given by our second property. And then our final simplification is 3x multiplied by the third root of 2x. Now again, our fourth rule says that we shouldn't have any radicals in the denominator. And the process of getting rid of radicals in the denominator is called rationalizing the denominator, and is probably the one that you're going to have to remember most when progressing through algebra. So let's tackle 2 more examples where we need to rationalize the denominator, assuming that x is positive. And in this case, we're going to be making use of the fact that the nth root of a to the power of n is just a. And so for the first example, assuming x is positive, the square root of x squared is just x. And so what we're going to do is we're going to multiply this by the square root of x over the square root of x, which is really just 1 over 1. Since any term divided by itself is just 1, assuming the term is not 0. Since any non-zero term divided by itself is just 1. And so here we get 4 times the square root of x all over square root of x multiplied by the square root of x. And that gives us 4 times the square root of x over the square root of x squared, which equals 4 times the square root of x over just x. So for the second example, it's the same idea, with the only difference being that we're dealing with a denominator of multiple radicals. And so all we're going to do again is multiply this by 4 times the square root of x plus the square root of 3 over the same thing. That'll give us 5 over the quantity of 4 times the square root of x plus the square root of 3 all over times the square root of x plus the square root of 3 squared, which comes out to be 5 times the quantity of 4 times the square root of x plus the square root of 3 all over 16x minus 3. And that's it. We'll close out this segment on radicals with a more general version of our first property. And to recall, when we were dealing with our properties, we required that a be a positive number. However, I was just doing that to make the examples a bit easier to deal with, and it doesn't need to be the case. So in this first property, this is being defined for if a is positive or negative. We'll say that the nth root of a to the power of n is a piecewise function where we have the absolute value of a if n is even, and then we just have a if n is odd. Now, if this notation here for the absolute value symbol is tripping you up, that is fine, since we'll cover that in future depth, and that all you need to know now is that the absolute value, which are the lines surrounding a, makes any number a positive. So for example, if you had the absolute value of -1, that would just be 1. And if you had the absolute value of -2, then that's just 2. So now for cases with this piecewise definition, if we have the 8th root of x to the power of 8, then that's the absolute value of x. And if we have the 11th root of x to the power of 11, then that's x. And for square roots, if we have the square root of x squared, then that's just the absolute value of x, since square roots hide the index, which is 2, and those two are the same number. Now we're going to move on to polynomials.